Now, good morning, friends. In chapter 14, Semiconductor Electronics, which type of the MCQ question can be asked in exam, either the competitive or the board exam, and how we can solve it. Already in Semiconductor Electronics, we discussed about the pure semiconductor, N-type, P-type semiconductor. Also in PN junction diode about the potential barrier and depletion region. And also we discussed about the logic gate. Generally the objective question depends on the conductivity of electron hole, that means the number density, and also on the base of the how much impurity atoms are added to form the N-type or the P-type semiconductor, and also on the base of the logic gate may be asked. So we are going to discuss about the some MCQ question can be asked in exam. Now first is, if an LED has to emit the 662 nanometer wavelength of light, then what should be the band gap energy of the semiconductor? We want to prepare the light emitting diode which emit the light with the wavelength 662 nanometer. Therefore, wavelength lambda is equal to 662 nanometer. That means the 662 into 10 is to minus 9 meter is the wavelength. What is the band gap energy? We have to find out the easy. So how we can calculate the band gap energy? Easy. For that purpose, we have the equation of energy E is equal to hc upon lambda. That is the energy of photon. Here the light is emitted as in form of photon. Therefore, the band gap energy EZ. EZ is equal to hc upon lambda. So this value we obtain in joule, but we require in electron volt. So first we calculate in joule, and then divided by the charge of an electron, we obtain the band gap energy in electron volt. Therefore, value of H Planck's constant 6.62 into 10 is to minus 34 joule into second into C 3 into 10 is to 8. That is the speed of the light in vacuum, and lambda is given as 662 into 10 is to minus 9 meter. So as we simplify, so we obtain 3 into 10 is to minus 19 joule. That is the band gap energy in semiconductor, which is used to prepare the light emitting diode. This light emitting diode can emit the light of wavelength 662 nanometer. And in electron volt, EZ is in electron volt is equal to EZ in joule upon E. Therefore, 3 into 10 is to minus 19 upon 1.6 into 10 is to minus 19. Therefore, 1.875 electron volt. That is the band gap energy for the given semiconductor. So that is the same equation as the energy of photon already we learned in chapter 12. Right? Now, EZ is equal to hc upon lambda band gap energy. We can calculate first the energy, band gap energy in joule. So by substituting the value of H, C and lambda, H is the Planck's constant 6.62 into 10 is to minus 34. C, velocity of light in vacuum 3 into 10 is to 8 divided by wavelength lambda is given 662 nanometer. Therefore 662 into 10 is to minus 9 meter. It is simplified. We get the band gap energy 3 into 10 is to minus 19 joule. Convert into electron volt. So this band gap energy divided by charge of an electron E. Therefore, 3 into 10 is to minus 19 joule upon 1.6 into 10 is to minus 19. 10 is to minus 19 cancel. 3 by 1.6 is equal to 1.875 electron volt. So that should be the band gap energy of a semiconductor. Clear? Okay. After that, on the base of the depletion region, the width of a depletion region is 400 nanometer. width of a depletion region D is given as 400 nanometer. 400 nanometer. Therefore, 400 into 10 is to minus 9 meter. The intensity of the electric field in this region is 5 into 10 is to 5 volt per meter. Electric field is given 5 into 10 is to 5 volt per meter is given. Then calculate. First, what is the potential barrier? That means we have to find out the potential in this region. And second is the minimum energy required by an electron to move from N-type region to the P-type region of the diode. That means we require the minimum kinetic energy. So we require the V and also the kinetic energy of an electron to move from N-type to the P-type region of the diode. So we know that the relation between the electric field and electric potential E is equal to V by D, or the electric potential V is equal to ED. So we know that E is equal to V by D, or in other words, V is equal to ED. Electric field and distance, so the length is given of a depletion region 5 into 10 is to 5. D is given 400 into 10 is to minus 9. Therefore, the answer is only 0.2 volt. 0.2 volt. Now, kinetic energy is equal to half mv square is equal to EV is equal to E. E already we know that 1.6 into 10 is to minus 19 into 0.2. So we obtain 3.2 into 10 is to minus 20. So 3.2 into 10 is to minus 20 joule. So this is the value of the minimum kinetic energy required by the electron to move from N-type to the P-type region, that is in joule. But how much kinetic energy required in electron volt? Therefore, kinetic energy of an electron in electron volt is EV upon E. E cancel, that means the only 0.2 volt, 0.2 electron volt. So that much kinetic energy required to move the electron from N-type to the P-type region of a PN junction diode. Now in this depletion region having the length is 400 nanometer, the electric potential is of 0.2 volt. We calculate from this because the intensity of the electric field is given and the width of a depletion region is given. So E is equal to V by D, therefore V is equal to E into D. E is 5 into 10 is to 5 and width of a depletion region 400 into 10 is to minus 9. Therefore 0.2 volt is the intensity of electric potential in a depletion region. Under this electric potential difference in depletion region, how much minimum energy required by an electron to move from N-type to the P-type semiconductor is equal to its kinetic energy. Therefore, kinetic energy is equal to E into electric potential V. Charge of an electron is 1.6 into 10 is to minus 19. Voltage is 0.2 volt. Therefore, 3.2 into 10 is to minus 20 joule. Right? But we require also an electron volt. Therefore, kinetic energy is EV upon E. That is in joule upon E. E cancel. Therefore, 0.2 electron volt. Now the next numerical, if one atom of arsenic is added per 10 is to 13 atoms of germanium, then the number of the free electron in 1 mole of germanium will be. We have to find out the number of free electron in 1 mole of germanium, right? Therefore, here per 10 is to 13 germanium atom, the one arsenic atom is added. Therefore, in 10 is to 23 atoms of germanium, how many atoms are added? Here is in one atom of arsenic is added per 10 is to 13 atoms of germanium. Right? Therefore, in 10 is to in 1 mole, that means the in Avogadro number, how much arsenic atoms are required. Therefore, we can add in 10 is to 13 atoms of germanium, one arsenic atom is added. Therefore, in 10 is to 23 atoms of germanium, how much arsenic atom is required? Arsenic atom added is 10 is equal to 10 is to 23 upon 10 is to 30 is equal to 10 is to 10. Now, arsenic is which type of the impurity atoms? That is the pentavalent. Therefore, per one arsenic atom, one per electron is obtained. Therefore, 10 is to 10 arsenic atom is required in 1 mole. In 1 mole, that means the 10 is to 13 atoms of germanium. Therefore, the number per electron in germanium is 10 is to 10 is equal to number of free electron. Now listen, that is also depends on our knowledge about the impurity atoms and also what is the proportion of the impurity atoms are added in germanium or the silicon crystal. So here, if one atom of arsenic is added per 10 is to 13 atoms of pure germanium, the number of the free electron in 1 mole of germanium will be, first thing, arsenic is the pentavalent impurity atom, that is the donor impurity atom. That means the per one arsenic atom we get the 1 free electron. Right? Okay. That means the per 10 is to 13 atoms of germanium, one arsenic atom is added. Now in 1 mole, the number of germanium atom is equal to Avogadro number. For simplicity, we only consider the power. Therefore, in 1 mole, or in other words, in 10 is to 13 atoms of germanium, the numbers of the arsenic atom added is N is equal to 10 is to 23 into 1 upon 10 is to 13. Therefore, 10 is to 10 arsenic atoms are added. But per one arsenic atom we get the 1 per electron. Therefore, in 1 mole, 10 is to 10 arsenic atoms are added. Therefore, 10 is to 10 number of the per electrons are obtained. Therefore, the number of the per electron in 1 mole of germanium will be 10 is to 10. Clear? After that, the same numerical again. If one aluminum atom added per 10 is to 9 atoms of silicon, then charge on hole in 1 mole. First, we have to find out the number of hole in 1 mole. And one hole has the charge equal to the charge of an electron. So this number of the hole is multiplied with the charge of an electron, that gives the charge of hole in 1 mole. Therefore, we can add like this in, that means the 10 is to 9 atoms of silicon. One aluminum atom is added. Therefore, in 10 is to 23 atoms of silicon, numbers of aluminum atom is N is equal to 10 is to 23 upon 10 is to 9. 10 is to 9. right? Therefore, n is equal to 10 is to 14 in 1 mole. Therefore, the charge Q is equal to n into E. So 1.6 into 10 is to minus 19 into 10 is to 14. That means the 1.6 into 10 is to minus 5 coulomb charge. That is the charge of the hole in 1 mole silicon crystal. Same numerical of earlier. For 10 is to 9 atom of silicon, 1 aluminum atom is added. Therefore, in 1 mole, we have to find out the charge of the hole in 1 mole. First, we have to find out the number of hole in 1 mole. Therefore, in 1 mole, or in other words, for 10 is to 23 atoms of the silicon, numbers of the aluminum atom is n is equal to 10 is to 23 upon 10 is to 9. That means the 10 is to 14. That is the number of aluminum atom. Aluminum atom is the acceptor impurity atom. Therefore, for 1 aluminum atom we get the 1 hole. So that much number of the hole are already present in 1 mole of silicon crystal. Now, what is the charge on this hole? So Q is equal to number of hole into charge of an electron. Number of hole is 10 is to 14. Charge of an electron is 1.6 into 10 is to minus 19. Therefore, 1.6 into 10 is to minus 5 coulomb is the charge of a hole in 1 mole silicon. Clear it? Okay. Now, next, in pure crystal of the silicon at 300 Kelvin temperature, having the numbers of atoms or the intrinsic charge density Ni is equal to 10 is to 16 per meter cube. If 10 is to 21 atoms of phosphorus added per meter cube, then the number of hole created will be how much per meter cube? Right? Therefore, we know that phosphorus is which type of the impurity atoms? That is also the pentavalent. So that gives the number density of the electron. Number density of the electron. Now we know that the Ne or the Ni is given intrinsic charge density 10 is to 16 per meter cube, and also due to the phosphorus, the number density of the electron Ne is 10 is to 21. 10 is to 21 per meter cube. Now we know that we have to find out the number of hole created will be per meter cube. Therefore, Ni square is equal to Ne into Nh. Therefore, Nh is equal to Ni square upon Ne. Therefore, Nh is equal to 10 is to 16 whole square upon 10 is to 21. 10 is to 21. Therefore, number of hole per unit volume is 10 is to 11 per meter cube. So very easy. Now listen, first thing, in pure crystal of the silicon at 300 Kelvin temperature, having the number of atoms Ni is 10 is to 16 per meter cube. So there is the number density of the intrinsic charge carrier Ni is given. Therefore, Ni is equal to 10 is to 16 per meter cube. Now, if 10 is to 21 atoms of the phosphorus added per meter cube, now phosphorus is the pentavalent impurity atom or the donor impurity atom. So per one phosphorus atom we get the one electron. Therefore, the numbers of the atom 10 is to 21 added per meter cube. So this value gives the number density of the electron. Therefore, Ne is equal to 10 is to 21 per meter cube. Then number of hole created will be. So what is the number of hole or the number density of the hole? So we know that Ne are given. Ni square is equal to Ne into Nh. Therefore, NH is equal to Ni square upon Ne. Ni 10 is to 16 whole square upon Ne 10 is to 21. Therefore, 10 is to 11 per meter cube. That is the number density of the hole. That is the number density of hole. Clear it? Okay. After that, there are 6 into 10 is to 19 electron per unit cubic meter of pure semiconductor. Now listen here, the number density of the electron is given Ne is 6 into 10 is to 19 per meter cube. What will be the number of the holes for this semiconductor of dimension 1 centimeter, 1 centimeter by 2 centimeter? That means the volume is given. So what is the total number of the hole? Right? Now, in pure semiconductor, first we find out the volume. Volume is equal to 1 centimeter into 1 centimeter into 2 centimeter is equal to 2 centimeter cube is equal to 2 into 10 is to minus 6 meter cube. 2 into 10 is to minus 6 meter cube. Now, in pure semiconductor is given. Ne is equal to NH. Number density of the hole and number density of the electron are same. That is given. That is the 6 into 10 is to 19 per meter cube. Therefore, the total number of hole in given dimension in V is N is equal to NH into V. NH into V. NH is 6 into 10 is to 19. Volume is 2 into 10 is to minus 6. So it's equal to 12 into 10 is to 13. That means the 1.2 into 10 is to 14. 1.2 into 10 is to 14. That is the number of holes. Again, here there are 6 into 10 is to 19 electron per unit cubic meter. That means the number density of the electron is given. So what will be the number of holes for this semiconductor of dimension 1 centimeter by 1 centimeter by 2 centimeter? The volume is 2 centimeter cube, convert into meter cube, therefore 2 into 10 is to minus 6 meter cube. Here the pure semiconductor is given. In pure semiconductor, number of hole and number of electron are same. Therefore, Ne is equal to NH is equal to 6 into 10 is to 19. Therefore, the total number of hole in given volume is N is equal to NH into V. Therefore, 6 into 10 is to 19 into 2 into 10 is to minus 6. So, we obtain 1.2 into 10 is to 14. Now, next. This depends on the mobility and also the conductivity. What amount of the impurity of atomic density is added to form the N type of semiconductor in germanium of conductivity sigma? Sigma is given pi ohm inverse centimeter inverse. Right? So convert into the meter, therefore 500 ohm inverse meter inverse. Mobility of electron mu E is given as 3900 centimeters square per volt per second. Convert into meter square, therefore 0.39 meters square per 1 second inverse. Now we know that conductivity sigma is equal to E into Ne into mu E. Number density into mobility. Charge of an electron into number density of the electron into mobility. What we require? What is the amount of the impurity of atomic density is added to form the N-type semiconductor in germanium of conductivity is given and mobility of an electron are given. We require the number density Ne. Therefore, Ne is equal to sigma upon E mu E. Sigma is given 500. E charge of an electron 1.6 into 10 raised to minus 19. Mobility 0.39. So as we simplify it, we obtain 8.013 into 10 raised to 21 per meter cube. That is the number density of impurity atoms is required to form the N-type semiconductor. Here we have to calculate the N-type semiconductor, therefore, here the number density of the electron is required. If you want to form the P-type semiconductor, so at that time the sigma is equal to E into Nh into mu h. So at that time we find out the number density of the hole. But here we have to form the N-type semiconductor, therefore number density of the electron or the number of electron per unit volume is required. Therefore, conductivity sigma is equal to E into Ne into mu E. Mu is the mobility, Ne number density of the electron, E is the charge of an electron. Therefore, number density of the electron Ne is equal to sigma upon E into mu E. As we substitute the value, we obtain the number of electron per unit volume is 8.013 into 10 is to 21 per meter. Right? So this type of the numerical may be asked on the base of P-type, N-type semiconductor. After that, we discuss our next question, MCQ question on the base of the logic gate.